So I'm Brian King, OpenPOWER IO Work Group Chair, and also work at IBM, working on IO and amongst other things. So I'm here to talk a little bit about some of my experience porting drivers to the Power platform from other architectures, and some of the issues that we tend to see both in the initial port and then also just regressions that creep in for drivers that already have been ported. So I'm going to start out today by covering just some basics of the Power architecture that relate to I/O. Areas like cache coherency, synchronization, memory barriers, load store ordering, PCI addressing, and extended error handling, things like that. Talk a little bit about boot on an OpenPOWER system, which a lot of you already are going to know, but just some of the nuances that means for I/O device drivers and such. Touch a little bit on test. We got a follow-up session on test, so I'm not going to dwell on that too much. I'll let Sachin give all the details there. But and then I'll kind of close out with just a little bit on OpenPOWER Ready and the I/O work group as well. So to start out with, byte order. So this is not quite, it's still an issue for some folks, but from a Linux perspective, we're rapidly racing towards Little Endian as the prime focus. If we look at all the OpenPOWER systems that are out there today, the vast majority of them are all running Little Endian. This reduces one of the barriers to portability. That said, obviously, if you're writing a driver from scratch, there's macros to make sure that the drivers are portable. So just continue to use the byte swapping APIs that I have there. The other thing, Power Little Endian is 64-bit only, so no 32-bit user space. And the only reason I bring that up is with a lot of I/O devices, sometimes they have management tools that have existed for years and years and years, and some of them are still 32-bit only. That doesn't seem to be too much of a problem anymore these days, but just wanted to mention that. And then the last item is just cache line size. We have 128-byte cache line size on Power. If you're doing micro optimizations of performance, that's helpful to know. We do have cache inject on P9, so doing smaller than cache line size DMAs aren't as painful as they used to be, but the 128-byte DMAs are going to give you the best performance. So let's talk about cache coherency a little bit. So if you want to, so one of the big things in a device driver is dealing with both cacheable memory and non-cacheable memory. And the cacheable memory is typically your memory in your host, DMA buffers, things like that. And the non-cacheable memory is typically your MMIO space, your bar space, your registers. And so you need to make sure that you're using the right APIs when you're accessing that non-cacheable storage, and you also need to be cognizant of ensuring synchronization between those things. And so we're going to dive into that a little bit here. Kind of the first basic macro is when you're doing MMIO stores. Typically, if you're going to a typical operation that a device driver does is they have a command block in host memory that you're going to fill out to tell the adapter to do something. You fill it out, and then you go and you poke a doorbell in the adapter. The adapter DMAs down that control block and executes it. On Power, you need to make sure that all the writes to that DMA buffer are actually in memory and not sitting in a cache somewhere. As long as you're using the MMIO macros like write-L to do that MMIO store, we have a built-in macro or a built-in hardware sync instruction in there to ensure that coherency. There is, not too long ago, the kernel community added relaxed variants of read and write. Today, those do the same thing on Power. There's some people that are going off and trying to optimize their drivers and putting in the real X variants where they think they can. Today, that's not going to buy anything at power, but not to say that it couldn't change in the future. But the raw variants, there's raw read and write as well. Those have no byte swapping in them and also have no built-in barriers. So if you are using those, you need to be very careful about making sure that you're using the right synchronization barriers. And we'll get into those, some more details of those in a bit. So there's a whole bunch of different ways to synchronize code in the kernel. We have spin locks, we have mutexes, semaphores, atomic variables, memory barriers, RCU, read, copy, update, all for different use cases. Some of them can be used in interrupt context, some of them can't. Some of them are very lightweight, some of them are more heavyweight. For the most part, I'm going to spend most of the time on barriers, just because that's an area that we run into a lot of problems with in Power. A lot of the other semantics are generally, as long as you're coding to those APIs and using those locks, spin locks and mutexes and such, we don't necessarily see as much problem in that area on Power. So I kind of broke out 3 different classes of memory barriers in the Linux kernel. So the first one is mandatory barriers, and these are always enforced. Today, these all translate to a hardware sync instruction on Power, which is a pretty heavyweight instruction. You don't want to just sprinkle these into your code in the performance path unless you really need one. But they do allow for synchronization not only between CPUs, but also between cacheable and non-cacheable stores. There's a lighter weight version of it, which is SMP conditional, and those are typically only used for CPU to CPU synchronization. Those translate to a lightweight sync today on Power. But those can't be used to ensure consistency between cacheable and non-cacheable memory. And then there's the DMA variants. These are still relatively new in Linux. These can be used so they don't get compiled out on a uniprocessor kernel, but they are lighter weight, they are lightweight sync, and so you can use them if you're needing to order loads within a DMA buffer. So if you have if the adapter is DMAing data and a valid bit, and you're reading those 2 values, you can use the DMA variant to ensure that you're checking the valid bit before you start loading something that's dependent on that valid bit. And then there's a link in the bottom of here. I've tried to put a lot of links throughout this PDF to other documentation that goes into a lot more detail. There's documentation in the kernel that goes into a lot of depth and a lot of examples about barriers and what you can and can't do, and is very platform agnostic. So there's some barriers that only apply to like Alpha or Spark. And so this tries to be agnostic and cover everything. All right, so I wanted to just kind of give you a couple of examples of some of the defects, some of the bugs that we found in device drivers having to do with memory barriers. So this is the first example. So here we have at the top, this is essentially an Ethernet device driver where we're processing the completion and take an interrupt, and we're processing the completion. So at the top, we check to see whether or not the command is completed. There's essentially a valid bit that gets checked there. And then we load both the producer index and the consumer index. Typically in a network driver, the producer index is managed by the adapter, and the consumer index is managed by the device driver, and they just kind of keep track of, in a ring buffer, what commands have completed. And so what is needed there is this read memory barrier at the bottom, because what that's attempting to order is making sure that the load of the completed bit up there at the top happens prior to starting to check the flags. The issue that we were finding was that the load of the flags at the bottom there was happening prior to the load of the completed bit, which was then causing stale or invalid data to be used, and it was confusing the state engine in the driver.
If I can interrupt, how did you find that problem?
This one, well, this one has been around. I did not find this one. This one wasn't around as an example for a long time. The next two are ones that I did find, and so I'll provide some background on those. So this is one that was found within the last month, actually. It's a bug that was around for a while. I don't know how long. And we just happened to stumble across it on a very large system with about a dozen of these adapters, with it's a 4-node machine, so Numa effects were very exaggerated, lots of memory, and so a synchronization, a hardware sync command takes a long time to happen. And so it was really extending and exaggerating a lot of the Numa effects and the load store reordering. So on the top is CPU 0. It's doing a transmit buffer. I pulled out a lot of the code here, obviously, but what it's doing is it's taking an SK buff, which is a network packet buffer, essentially, and storing a pointer to that in a local buffer that it managed for the transmit packet. Does the right memory barrier to ensure that the whole packet data and all the metadata that's associated with that the NIC needs to know about is synchronized. Does a doorbell, which is just the non-cacheable store to the adapter, and then the adapter goes off and starts processing that. On the bottom is the interrupt path, and here I pulled out a lot of the code here too. There's a surprising amount of code that happens, and it really boggled my mind when we actually stumbled across this one, because what we were hitting was line 14 down there. We had a null SKB pointer in the transmit path. And if you roll back, in order for that to happen, what was happening was that the hardware consumer index, that load is a load that was being delayed. We were speculatively walking through down into the while loop and loading and falling down and loading the SKB on line 11 there before we loaded the hardware consumer index to see that we should be processing it. And so we're getting down to line 11 with a null pointer. And one of the questions that came up when we were looking at this was, well, why didn't that line 12 oops or hit a null pointer there? And so I had to write a little bit of test code on this one. And the prefetch macro on power is essentially just a data cache block touch command. And so all that's happening on that line 12 is it's taken the SKB address, which is null, adding the offset of end into that, and then taking that as the address, passing, which is some integer value, let's just say 200 or something like that, and passing that to prefetch. Well, that instruction is essentially just a hint to the processor that, hey, we might be pulling this cache line in. Perfectly valid to give it an invalid address, and it just doesn't do anything. And so the fix here was between lines 6 and 7 to insert a SMP read memory barrier, and to make sure that we load the hardware consumer index before we start marching down and loading any the SKB pointer and other things. We're still trying to reproduce this one in our lab, but we did confirm that we were hitting this problem just left and right on this one machine, and with the fix, all the problems went away. It was an interesting case. The third,
Like there should be a best practice in there somewhere, especially given the while loop, right? I mean, the while loop is sort of a trigger. You're waiting for something,
yeah.
and you've obviously set it up with things at the top.
So this is a third and final case that I'll describe. This is one that we found early when we were bringing up Power 9. And this is a device driver that we used on Power 8, no problem. Power 9, it was just aggressive enough that we encountered it. And it's somewhat similar. On CPU 1 here, we have sending it, it's once again sending a transmit packet, save away the SKB pointer into our buffer, do a write memory barrier to ensure all our stores are coherent across until we get to 5, and then we do this next to watch pointer, which points to essentially the next transmit descriptor to process, and then we'd ring the doorbell. And what was happening on the right-hand side was something somewhat similar. The Intel driver had this read barrier depends, and that's what they were going to, they were trying to use that to ensure that the load for that EOP descriptor happens, loading from that next to watch happened before we went off and checked the status bit. But that is not sufficient on Power. That barrier does nothing on Power. It's a no-op. It does nothing on any architecture except for alpha. And so what we ended up having on this one was we came down and it manifested itself as calling NAPI consume SKB on a stale SKB. And so we were having random crashes. We were having, it looked like an issue of, we were blowing up in just very strange places. And so we turned on, memory debugging and, found that we were indeed accessing memory that had already been freed. And we, narrowed it back to this SKB, and we, stared at the code for a while and came to the conclusion that we needed a barrier there.
It says static code analysis tools.
I'm not aware of any static code analysis tools that exist today that would do this. I don't know that it would necessarily be impossible, but
So, for example, you said the read barrier that doesn't do anything on Power. So, is there a way maybe through some tool we can inspect that and find that out?
I think the challenge would be for the static analysis tool to understand enough about the interactions with the hardware and what those different loads were doing to be able to detect it. I'm not an expert on static analysis tools, so I don't know how difficult that would be to do, but it's a good question.
Oh, yeah.
Question on that, on the debugging side. If you were using, how did you isolate the problem? Have you been using kernel facilities for this, or just kernel prints? Because I don't know if the print key is actually going to affect the
Yeah, so we were very dependent on getting a K-dump from this to actually do the deep analysis and understand that. And then once we, and like I said, we also turned on some memory debugging in the kernel that would check for using freed memory.
Yeah, the question I was going to ask you was, the question I was going to ask is, in your experience, what's more common, a missing barrier or a barrier of the wrong type? I mean, because this second one is they had the right idea.
Right.
They just.
I would say it's the missing barrier. That's usually the problem. And of course, this bug was not only in IXGBE, it was in every Intel driver that exists in the tree. Because they seem to take one, copy it, and copy the same bug. And so we went and fixed them all. All right. So we're going to lighten it up a little bit. after diving in deep there. I want to talk a little bit about PCI address translation on power. We have, in a KVM environment, we use TCEs. So any PCI pass-through device, SRIV device gets passed back to a guest. All the DMA buffers that get mapped and used by that adapter use these translation control entries, and it's essentially just a map that translates an address that you can give on the PCI bus to a physical memory address, and they have permissions associated with them, whether that be read-only, write-only, or read-write, and we tend to now and again encounter, usually when we're bringing up a new adapter, sometimes the devices will behave oddly because they'll go off and DMA read request for some random address. I've seen that happen before. So the IMU has different TCE sizes it supports. 4K is the default. There's 64K, and then depending on the processor generation, there's other sizes as well. So obviously with the TCs, there's a certain overhead involved in mapping them and unmapping them, and we try to mitigate that when we can. So in a KVM PCI pass-through environment, typically what we'll do is we'll take, when the driver sets its DMA mask to say how many bits of addressability it has on the DMA bus, if it supports 64-bit DMA, we'll go off and basically try to allocate enough TCs for the entire VM's memory, map them all, and then we just do a simple lookup and don't have to do any H calls to map and unmap. That improves performance quite a bit. If the device doesn't have support for 64-bit TCs, then we fall back to like a 32-bit, the default 32-bit window. And we put some, I'll talk about it on the next chart a little bit, on some of the hacks we put in for bare metal to try to make life a little better for the devices that don't support full 64-bit. And then for the smaller DMA windows, when we do have to do maps and unmaps, we basically taken the DMA window and then hashed it across the CPUs so that we don't have one lock that we're contending for when we do maps and unmaps, and we can do more in parallel. For bare metal, as long as the device supports 64-bit DMA, we don't use TCs at all. We will use what's called this no translate and direct addressing and bypass the TCE. Now, however, this doesn't mean that the DMA address equals the physical address. Bit 59 is on. But you need to make sure that you're still using the proper APIs, mapping and unmapping DMAs. This is also one of the things that we come across sometimes on bringing up new adapters. They just have the assumption that, hey, on Intel, they typically start at address 0 and go up to how much memory they have. And with us, it's different in the fact that all our DMA addresses start with bit 59 on and higher, at least in bare metal. On Power 8, we put in some support for a TCE bypass window, and so if a device supports less than 64-bit DMA, we'll essentially allocate a big DMA window with 256 meg TCEs and essentially allow it to address all the system memory with that one window, and it doesn't have to, address, the high bits of the DMA. We're trying to implement something like that on Power 9, but the architecture is different, the PHP is different, and so there's kind of a work in progress there. It's looking like we might have a way to do up to, if a device supports 48 bits, then we can do that. But I put this in as an example just because I occasionally get asked questions about write combining. If you have a big bar, the Mellanox driver has a good. I just pulled this out of the Mellanox MLX4 driver. They've got essentially a bar window, a large bar window that they can use to send really small packets, and so they'll send them with write combined MMIO writes rather than trying to do the whole handshake with a write a doorbell, do the DMA, and so if you want to do something like that, this is a rough outline of the steps involved in doing that. Okay, EEH. So obviously this is a big platform difference with other architectures. This is something that's unique to Power. It's a feature of the PCI controller. If we hit a parity error, or if we hit a DMA to an invalid address, or there's a lot of different errors that can cause an EEH. And so when this happens, the device goes into what's called a frozen state. Any writes just go to a bit bucket, any reads, you get an all ones response, and DMAs are essentially shut down. There's code in the platform layer of the kernel to filter that all ones load response, and then if it sees that, it goes off, makes another call to check, well, is the slot an EEH, and if it is, then it'll go and kick off some EEH recovery. And there's kind of two different paths that you can go down. Either your driver is EEH aware or it's not, and we try to recover in both scenarios. So if it's not aware, this means that there's been no code written specific to EEH recovery in the driver, and we simulate a hot plug event. So we do a hot plug remove to detach the device, recover the slot, and then hot plug add the device back. This works okay in some scenarios, if it's an Ethernet driver, if it's a driver that you're not booting from, maybe. Storage drivers don't really work too well with this recovery model. Then it can work. This is certainly another area that we do find expose issues in device drivers as well. Some drivers, you try to hot plug remove them, and they can't talk to their adapter and get reasonable responses back because their writes are going into a bit bucket and their loads are all coming back all ones. Sometimes they just blow up in spectacular ways. So the answer, obviously, is either to fix those bugs or to put in EEH handlers. And the latter is preferred, clearly. So to implement EEH recovery in a driver is not that much work. There's essentially in the PCI driver struct, there's a few handlers a few function pointers that you can implement to allow your driver to participate in the EEH recovery process. The first one gets called, error detected, gets called when an EEH gets detected. And then the driver can influence what happens as part of the rest of the recovery, whether it needs a reset to recover, or no, it was able to recover it all on its own, or whether it's just, doesn't think it can recover at all. There's an optional MMIO enabled one, so not many drivers use this. If you want to try to extract failure data out of your device, before it's been reset and cleaned up, the EEH driver will re-enable MMIOs, so you can go and try to pull some of that information out. And that's called next. And then the slot reset one gets called after the EEH recovery has completed, but prior to resuming normal operations. So, typically the error detected and the slot reset are the ones that, typically get it implemented the most. And then the resume gets called after recovery's all done and everything's back, and and IO is able to get sent again. You have a question?
Yeah. Do we have, or do we publish a template or best practices for what these various routines would do? Or are there drivers we can point to that say, do the right thing or nice in this area? It would seem like this might smack for at least some starting code in an area.
Yeah, so there's In the references section of the presentation, there's a couple links on, one of them is, there's a couple in the kernel documentation where they go into quite a bit of more detail about all the APIs, how they get used and when they get used, and what, you know, what to do with them, how to implement them.
Cool, thanks.
A little bit about reset. So the Eeh Recovery code uses hot reset to recover the slot. There are some devices that it doesn't always work for one reason or another. And if your device is one of those, there's a workaround that was put into place. There's a flag that you can set in the PCI device structure to say that you need a fundamental reset in order to recover. And so if any devices within a PHB that encounter any EH have that flag set, then that whole PHB gets a fundamental reset as part of recovery. And then I put a couple more tips in here. If you ever want to disable EEH for some reason, that can be done through debugfs. If you disable it, what happens is essentially the card goes into EEH state. It's just not going to come out. And you're just going to be stuck with that slot frozen. But if it's choosing between that or your driver blowing up, then maybe that's an okay option. Two other comments on EEH. One, if you want to inject, actually, if you implement this, you want to test this, this is how you test it. It's in debugfs. There's more details on this also in the kernel tree, in the kernel source tree, which I have a link to later in the presentation. But this is, you know, at a high level. There's, you know, sysfs parameters that you just toggle the air inject bit and toggle it off. And there's different flavors of air inject that you can actually do, whether that be, you know, there's different causes for EEH. Generally speaking, this is sufficient to validate most device drivers. And then we do have recovery limits associated with EEH. If you hit 5 in an hour, we disable the device and it doesn't come back. So if you're testing EEH, you can work around that by increasing that in debugfs. All right. Most of you probably know most of this already. In PettyBoot, obviously there's the Linux kernel booting there. Does auto detection of the boot devices. For I/O devices, if they have specific tools for managing them, if they're open source and they're sufficiently small, we can pull those into the PettyBoot image. And so they're just available there. You can exit to a rescue shell and access them. We did that with the IPR RAID controller, for example, and you know, and we have other tools in there too. So, and then there's the plug-in architecture. If you have a tool that doesn't meet those scenarios, but you want it easily consumable, I put a link down there at the bottom for how to use the plug-in architecture and port your tool to that. And that just makes it just easy to kind of pull the tool in, use it in the rescue image before you boot your system. And there's PettyBoot, which I'm sure you've all seen. So one of the key things that affects drivers as part of this whole boot process, which is different than x86, is we are heavily reliant on KExec, which is a kernel feature that allows you to have one running kernel here, load another one in memory, and essentially simulate a shutdown on the old kernel and jump to the new kernel in memory with no real hard resets or anything going on. So to a device driver, not all of them are they're not used to handling that transition all the time because there's no PCI device reset. And so you know, bringing up new devices in that sort of environment, this is something that you know, devices typically need testing on and hardening in. And this isn't power specific. This is a feature that exists in the existing Linux kernel. You can run it on x86. You can find all these same bugs there. It's just that it doesn't necessarily get tons of testing on x86. You know, in the shutdown path, you know, if you are trying to get a driver working well in this environment, you know, in some drivers we've tried to optimize it so that it's aware of this whole flow, and so it's because the more heavyweight that shutdown is in the KExec, the more it's going to slow down the whole boot. You know, if you're aware of that transition, you can just kind of pause the adapter and bring it back to life on the other side. But this needs more testing across the board. Which leads me into my next topic, test. So some of the areas, these are some of the, I just tried to list out some of the areas that we see problems in on a regular basis with I/O drivers on power. KExec, we already talked about. KDump is another one. EEH is another one which we already went through. PCI hot plug add and remove, surprisingly, we still see issues in this area. I think we just exercise it more than others do on other platforms. CPU online, offline. I think that our biggest pain here has just been in Linux block MQ. They've with the NVMe driver, and they have all these threads and all these interrupts, and you start offlining CPUs, and they start moving things around, and you know, and a lot of that code is just under such heavy development. It's been a little bit of a problematic area. The community is definitely well aware of it. There's patches that go in all the time, hardening this and trying to optimize it. KVM direct I/O assignment. So this is your PCI pass-through in a KVM environment. Function level reset is really highly desirable if you want a device that's well supported in this sort of environment. And please don't make a device that's advertises support for function level reset, but actually doesn't do the right thing when you do it. That's probably the worst of all scenarios, and we see it too often. The stress testing with data integrity checking, and then just continuous upstream testing. That's something that we need to figure out a better way to do that as a open power ecosystem. Once we have a driver working on power, how do we make sure it stays working on power and doesn't regress? All right, I got two more charts, and then we'll open it up to questions. So one is OpenPOWER ready. There's a whole nother session on that earlier. I just wanted to put a couple links on here. We got about 82 I/O devices that are OpenPOWER ready today. And there's the link if you want to, the resource catalog's on the bottom if you want to look to see what those devices are. And if you've got a new device to try to get through the process, there's the link there. And then I just wanted to have a shout out to the I/O work group. I just put the charter in here along with a link to the work group and a link to how to join the work group. If you're interested in enabling I/O devices on power or any of these topics, I encourage you to join. We meet monthly and talk through all these sorts of issues. So. And then this is all the links that I collected as well, so that might be of interest.
I want to see if there's any questions, but I do have one for you. I didn't see page size
as that's a good one.
Listed item on your list.
Yes, yes.
We're different.
We are
How often
different.
does that filter into drivers?
It does filter into drivers on occasion. Our base page size is 64K as opposed to 4K. There's oftentimes device drivers that make bad assumptions. There's one Intel Ethernet driver I can think of that allocates way more memory than it should because it's allocating a page for each SKB, and that's a lot of memory.
Okay. Any other questions for Brian?
Thank you very much. I would like to ask you something regarding how KVM would use the memory. So imagine in the context of OpenCAPI, for instance, now what we're doing, we need to create a memory address range, a physical address range, then we create pages on top of that using libcxl, and then we create a memory backend in QEMU, passing a pointer to KVM to actually map this memory as a normal system memory. And then KVM, we're still investigating what happens, but KVM doesn't like that on Power. We have done it on ARM and it works, and it considers, I think, the memory as device memory. Do you have any idea, any insight, or where we should be looking? Sorry for that.
That's a great question.
Let me take your name, and I will connect you with
Yeah,
the
okay.
OpenCAPI
Sorry
folks
for,
there.
I thought, yeah, thanks.
Yes, yes.
Oh, we got another one.
Hi. So the question is, I was trying to do some like KExec inceptions, KExec after KExec.
Yep.
And every time I do, like first KExec happens after PT boot, and after I do the next one, the USB-free like XHCI driver always falls apart. Any pointers how to start debugging it? Just like where to look, keywords, anything. It happens all the time. The kernel is like 5.2 to like recent one.
Right. So there's clearly something in the petty boot kernel that's not in the kernel you're booting, or a difference there, right? Because the petty boot works, but then the follow-on boot does not work.
Yeah, PT boot works. It sees USB devices. The kernel that it boots also works. But if I boot the same kernel, I boot it once more through KExec, like for fast reboots, no longer works.
Right. So if I play the back, the booting from petty boot to the 5.0 kernel works. The 5.0 kernel to the 5.0 kernel does not work, right?
Yes.
So
The boot works, just the USB-free driver just blows up.
Right, right. So it's likely in the shutdown path of the XHCI host controller
PCI,
code,
yeah.
would be my guess. And so if you can compare, that shutdown path with the shutdown path in the 5.0 kernel, there's likely some difference there that's you're tripping out over.
Thank you. That's a good pointer. Another one. Quick one.
Oh, yeah, sure.
Yeah, my use case may sound strange to you because I use like OpenPOWER as a workstation, as a development one, so it's like my desktop. I was trying to get some sound on it. It was EMU10K1 card, and basically it requires some certain kernel options I couldn't enable on Little Indian 64-bit kernel. It refers to one thing. I don't really understand what it is. Maybe you can shed some light. It's called zone_DMA. To enable this, you have to configure kernel for like small books, like embedded processors, and I think it has to be big Indian pretty much.
Okay. What's the behavior when the driver loads?
Sorry. On a recent kernel, you can even select it in menu config, but on like 4.14 kernel, it just cannot talk to device. It's an old device, old chip from early 2000s, and I think it has 31-bit DMA, something like that. So the real question is, what is zone DMA? If you can like explain, like I'm 5.
Sounds like you need 2 emails.
Yeah. So there should be no zone DMA. I mean, that's kind of a legacy thing for x86 with when there's DMA restrictions. So not on a power box, all the memory is DMAable. There is no unique sort of zone DMA. So we'd have to dig in a little bit more to understand what you're running into. One of the things that since this is an old adapter, this is probably the case, but another thing that we tend to run into, we've hit on a couple of, we ran into on some graphics adapters, some of the AMD ones, they support up to 40-odd bytes of DMA, and also on the same thing on the audio function, and that also applies to their MSI vectors for interrupts. And so there are some workarounds that are put in place in the kernel to handle that too. But I don't think that's, I think if you're hitting that, you would have probably, your kernel would have crashed. But, so I think we need, yeah, I'll take your name, we'll see if we can help you.
Sorry, one
third one.
last one.
You really need his email address.
Sorry, I'm just started doing this.
No,
it's
no,
kinda,
this is good.
It's the person who probably can shed some light on it. So on the I/O side of things, like connectivity, USB 3.1 is non-existent currently on Power for us because pretty much all the controllers are based on that S-media chipset. And it always gets shut down because of its like errant DMA access trying to do this. It just gets taken off the system. Are any workarounds even possible, or it's just like broken by design?
So I don't know that we've, I don't know that I would go so far to say broken by design. I would say that you're probably at the forefront of trying to get USB 3.1 working on Power. It's not something that, you know, that my team or anything has really tried to do. So,
But Brian, we do know the Red Hat USB maintainer, a former IBMer, now recovering as she's come back into IBM. So we may be able to get some help on this sort of problem. So once you get his email address, we should probably talk to Therese and see what we
yeah.
Yeah, I used to
Debugging that
be
piece.
myself. So.
Well, thank you for your support. All right, any other questions for Brian? If not, I think we've run over a little bit. Thank you very much, Brian. Excellent information. Let's give him a round of applause.